Okay, we're going to start with factoring difference of squares. First of all, let's talk about what is a difference of squares. So a perfect square is where we have something times itself. Now you can see right away that these are not perfect squares. This one's a minus, this one's a plus. So they're almost identical except for the sign. This is a difference of squares. They're perfect squares with different signs. Small difference. Now, when we use the distributive, when we FOIL this out, we will end up with, now the middle terms, we're going to combine them because they have like terms. They're both x's. We can't combine the x squareds, but we can combine the x's. And what we see is the middle terms disappear. That's the nice thing about the difference of squares. The two middle terms cancel, and we finish with a binomial. It's the only time we finish. We start with two binomials and finish with a binomial. Now the key thing is in factoring, notice that if we want to go backwards, we just take the square root. Square root of 9 is 3. Square root of 81 is 9. So if we're doing difference of squares, we just have to use that shortcut. We have to recognize that it's binomial, there's a minus sign, and there's perfect squares on both ends. That's the key. So if we have that, we square root both ends, and we get x and 3. Now the only way we get a negative 9 is x plus 3 times x minus 3. Negative times positive is a negative. The two middle terms will cancel out. We end up with a binomial. Same thing here. We've got two perfect squares, we have a minus sign, and it's a binomial. So I square root both ends. I get 5 and g. 5 plus g, 5 minus g. Doesn't matter which one goes first. It could be the minus first, the plus second, or like I've got written here. Order does not matter for multiplication. Now this one's a little trickier. We can see 49 is a perfect square, but it's f6. Now 6 is not a perfect square, but we can break this into f3, f3. The square root of f6 is f3. So we just need an even number on the exponent and a perfect square on the number. So if we take the square root here, 7. So I'm going to take my f3 and 7, put them together. f3 plus 7, f3 minus 7. Now the most important thing in difference of squares is being able to recognize them. Now all of these are binomials, but are they difference of squares? So let's take the look at the first one, 144/25. It might actually be helpful to practice your perfect squares, and you can write them on your page or your quiz. Before you start. Typically we go up to 15. That you're expected to use. So if we have this list of numbers, we can see 144 is the perfect square. 25 is also. x4 is an even exponent, so we can break it up into x squared and x squared. It works. It is a difference of squares. This one here, we've got a perfect square, perfect square. This works, it's even. E. There's an invisible 1. We cannot square root the h and make it work. So this is not a difference of squares. You have to have even exponents on all variables. And this last one, 20 is not one of my perfect squares. 45 is not. So we can't do this one. But here's the trick. We can do a GCF. If I look at these two numbers, 5 goes into both of them. If I remove the 5, I now have perfect squares. So this is, but it's hiding. So always remember, GCF first, if you can, remove something, and then take a look and see if you can do even more. In this case, we factor GCF, and then we factor difference of squares. So let's do some examples. I'll show one and then pause the video, try the next two on your own. So, perfect squares, everything works, binomial. So whatever you get from there is repeated in both binomials, 1 minus 1 plus sign. It doesn't matter the order. Binomial. Variables are even exponents, perfect squares. It works. (5p) and 12t will be repeated. There we go. This last one, we don't have perfect squares. We can take a look. GCF 3 goes into both of them. Now we have perfect squares. We have a binomial. Actually, wait a second. x3 is not a perfect square. We cannot do difference of squares when the exponent is odd. So this one would finish with just GCF, and we're done.